we've seen that in order to get economic growth in the standard model, because there are decreasing returns to scale to the accumulation of physical capital, therefore we need productivity change in order to drive economic growth. Next, we want to try and understand what drives this process of economic growth more deeply. Now, there are going to be, therefore, two ways of trying to get economic growth to occur naturally in this model without just assuming that something is driving it exogenously. One is going to be to get rid of decreasing returns to scale in accumulable resources. How are we going to do that? Well, we'll see in a minute. The other is going to be to try and model explicitly why it is that productivity change might occur. Maybe due to some sort of innovation, for example. We'll get to that later. So now it makes sense to turn and start to think about models of endogenous growth. Models where growth isn't just assumed, or the factors powering growth aren't assumed, rather they are explicitly modeled. Now, the reason why we have to rely on productivity rather than the accumulation of inputs to get economic growth is because there are decreasing returns to scale in accumulable inputs, that is, physical capital. But what if there were not? What if our production function looked like this? What if we just set alpha equals 1? If we do that, we would end up with what's called an AK model of growth. And you can see why it's called that. It's because, of course, AK is just the production function. Now, there are two ways to try and do this sensibly. One is to say that rather than there just not being labor in the production function, which seems a bit silly, how about instead we think of labor itself as a form of capital, human capital, now labeled H. In other words, it too is an accumulable resource. So then, whereas before we had that KT plus 1 equals 1 minus delta K of T plus investment, now let's label investment with K so that we know that it's specific to physical capital. Alongside this, we have human capital, which accumulates in exactly the same way. In order to distinguish these two depreciation rates, let's call one delta K and the other one delta H. So what's going to happen now? Well, let V of K and H, now we have two state variables, capital of both kinds, be the max of, well, let's assume that this person has log utility as before, straight to the recursive formulation. And rather than having time subscripts all over the place, let's just say that capital tomorrow and human capital tomorrow are K prime and H prime. So let's say the person is maximizing this. Subject to what? The usual condition that output must exceed whatever expenditures or uses of output the agent has. One is consumption, of course, but now we have two more. One is investment in physical capital, and the other is investment in human capital. This must be less than or equal to output, which is this. In addition, we have these two constraints. And of course, we can plug them in here, and we'll just end up with one constraint, which will have this form. Right. Next, first order conditions. We're going to have a very simple first order condition for physical capital, which is that the derivative of utility is going to be this times the first derivative of the value function. And the first order condition with respect to human capital tomorrow is going to look extremely similar. The only difference is that this is going to be the second derivative. There was a little mistake there when I said the first derivative of v, what I meant was the derivative with respect to its first argument, and when I said the second derivative of v, I meant its derivative with respect to the second argument, which is human capital. Next, we need the envelope condition to try and figure out what these derivatives are. The envelope condition for physical capital is going to be, again, well, it's the derivative of the utility function with respect to consumption times the derivative of consumption with respect to capital, which of course is the marginal product of, in this case, physical capital plus 1 minus delta k. And the condition for human capital is going to be much the same. The only difference, of course, is that it's the marginal product of human capital that we have here. Of course, this is delta H instead. Put this all together and we get two Euler equations. One is going to tell us that C prime over C is beta times alpha A K I guess let's do this. This is going to be K today, then this should be C today, and this should be CT minus 1. That way we don't have to label everything with a time subscript or with a prime. And for the human capital Euler equation, just of this. Of course, since the left-hand side of both these things are the same, we can set them equal to each other. And we'll find that in equilibrium, this condition must be satisfied. And if you look carefully, you'll see that what this condition does is that it actually pins down the ratio of the two forms of human capital in this economy in equilibrium. So there always has to be a certain ratio between physical and human capital here. To be precise, what I mean is in equilibrium, there is going to have to be a fixed ratio of human capital to physical capital at any date in which those variables are chosen. At date 0, of course, K0 and H0 are given, and they may or may not happen to equal that value, but in all periods thereafter, immediately they will set themselves so that ratio is established. take an example where the two depreciation rates happen to be equal to each other, then this condition becomes very straightforward, because this cancels out with that. And then, of course, this disappears. And, well, that cancels. We end up that the ratio is just the same thing as the ratio of the income shares. Now, let's just go with the simple one and plug it back into here. Doesn't really matter which one we choose. And what we're going to end up with is that consumption is growing, because what we have here is the growth factor of consumption by this amount. If we're not looking at this special case, it will still be the case that this pins down some ratio, which when you plug into either of these conditions is going to pop out some number. And of course, this number, if your parameters are correctly chosen, will give you something greater than 1. And if it does, we have endogenous growth, where the growth factor of consumption is some number that depends on these parameters. Thus, we've achieved endogenous growth, essentially by saying, well, okay, let's say that labor is actually an accumulable resource as well. Notice that in order to get growth this way, you need basically the exponents on all accumulable resources to add up to 1. It's something that some people call the curse of linearity. The production function essentially has to be linear in accumulable resources. If it isn't exactly linear, if these things don't add up to exactly 1, then it's not going to work. Which suggests maybe this is kind of a knife edge condition. Whenever your model depends on a knife edge condition in order to work, that's suspicious. It probably means you're missing something, and your model rather is missing something. Another way in which we might get economic growth is, what if there are externalities? What do I mean there? Let's go back and find our production function. And let's go back to the original formulation where this is some labor which is available in a fixed amount or in an amount that grows over time with population, but it's exogenous. And let's say that, remember, we have a large number of identical households, each of which has some capital K. Let there be something else called K bar. What's K bar? K bar is the average holding of capital across agents, or the total. We're going, for simplicity, going without population growth, so of course the average and the total are the same. And there is some exponent here. So when agents maximize and choose investment, they take this as given. Now, so far I've been looking at the planner's problem, but still, what we can do is say that the market problem is going to be the same. I'm going to have the same solution as the planner's problem if we assume the planner is a little myopic and doesn't realize that when he or she chooses K, that it actually also results in a choice of K bar. That's what makes it an externality. Agents either have no control of it, or maybe they don't realize that it's there. Either way. So they take it as constant. Although, of course, it isn't. They may understand that its evolution affects them, but the point is that when they make their decisions, what they take into account is this exponent alpha, not alpha plus psi. So that, of course, means that the planner's problem, if the planner were to understand that psi is there, that K bar is here, rather, that planner's problem will not be the same as the solution to the market or the solution of the planner if they don't realize that. All right. So let's just suppose n equals 1 as before. So we drop it because maybe it's available in a fixed quantity, 1, and it doesn't enter the utility function, so the agents will set it to 1. This will give us a very easy value function, which depends on k. Again, let's go with log utility. Discounting k prime. Subject to the budget condition c plus k prime. So again, we're smooshing the budget condition or feasibility condition and everything else together. Subject to this production function, k bar plus 1 minus delta. Okay. Now, the Euler equation that we get, skipping a few steps, is going to be different. It's going to be CT. So this is the growth factor of output, well, of consumption. Is going to be beta alpha A K bar plus 1 minus delta. And of course, the way this is written, it's not clear how we're going to get economic growth at a balanced rate, because for this to be a constant, we would need this to be a constant, but of course, capital is going to be growing at the same rate as output. There is one way, of course, to do that, and that is the following. First of all, remember, in a symmetric equilibrium, K equals K bar. So if we set that equilibrium condition, remember, you can't do that until after you've taken the first order conditions. That's the nature of this being externality. So now we have just K there, and that means is that we have just K plus, sorry, alpha minus 1 plus psi there. So again, we have the problem that K is in this function, but there is one special case where, of course, we can get K to disappear, and we'll end up with a constant growth factor for consumption and everything else here. And of course, that is what if alpha minus 1 plus psi equals 0, which of course is the same thing as saying that alpha plus psi equals 1. Then this whole thing is 0, and it disappears, or it turns into 1. And so again, we have a endogenous growth mechanism here, which again depends entirely on linearity. The exponent on capital if we include the externality, has to add up to exactly 1. The curse of linearity returns. So we don't need anything to get economic growth through productivity accumulation in neither of these two frameworks. But again, it does rely on this assumption that, on this knife edge condition, that the accumulable resources actually have an exponent of 1. The production function is exactly linear in accumulable resources, which of course makes us think maybe this isn't very general, maybe this isn't very realistic. So maybe what we need to do is go back to a framework where we still have decreasing returns, but again, need to rely on there being some form of productivity change. And for that, we will need to look at some very different kinds of models. Now, before we move on, there is one thing we can do here, which is to consider, what if there were a social planner who was trying to maximize welfare in this economy and who was able to take into account the fact that k equals k bar in equilibrium? What would happen then? To look at that, all we need to do is maximize this function with respect to, maximize this function with these constraints, taking into account that equality, which basically means that since they know that that's what's going to happen, they are able to just take this function and set k equals k bar right from the get-go. Of course, all that does is mean that we get this. And since they take it into account, it means that the Euler equation for a social planner who knows this and sets this equality in advance, takes it into account, is going to be slightly different. It's just going to be that. Now, when we impose this condition, which of course is still required for us to get balanced growth here, this again will become 1. But you can see that this condition and this condition are not the same. Of course, this is equal to 1, and this is alpha, which is something less than 1. So in this environment, you will have that the optimal growth rate, the one that takes into account the externality, is one that is going to be faster than the market growth rate. In general, in models of economic growth, there will be various different forms of frictions. In this case, it's an externality. In other models, it might be an externality of one kind or another, or an informational friction or a search friction. In either case, it's not always going to be true that the optimal growth rate is necessarily higher than what emerges from the market. So that's important to keep in mind going forward.